health system scale language models are all-purpose predicting engines. Are they? Let's find out. Hi, I'm Junaid, neurocritical care stroke and epilepsy specialist, and today we're going to talk about this particular paper that came out. This is, again, a very fascinating paper in which the claim is that all-purpose, and this is very important in understanding what they mean by all-purpose and then predicting engines. And that's what we have been talking about in terms of what really artificial intelligence is all about. AI is all about a prediction engine. It is about predicting. Large language models basically predict the next word after your current word. So, literally they go word by word. Fascinatingly, literally every single word is predicted from the previous sentence. So it is all about prediction. So what they are doing over here in this particular paper is that physicians actually have decisions, right? That's what we do. And sometimes, especially in high involvement situations, physicians have to do what we call, they get even decision fatigues. So they are constrained by decisions every day. And existing data structures like clinical prediction tools have limited use in everyday practice. Now, what do we mean by that? So if you go back and say, if you're going to go like this ABCD2 AI for TIA score, what we designed these calculators for was to predict the outcome of the patient. And this was done by traditional systems in which we had the structured data. That structured data, we put it into the calculators, and that structured data will give me a prediction. So for example, if the patient is 60 years old, he has some speech disturbances that lasted for this. Now I know that this is 4 points, and therefore the 2-day stroke risk is about 4.1%. That's the prediction, and that's what we want, because it changes the game completely. If the patient is going to be admitted or not, if the patient is going to have dual antiplatelet therapy or not, if the patient is going to have a closer follow-up or not. The way things measured are exactly what we do all the time. We are trying to predict the risk. And we have been doing this for a long time in terms of this structured data. And that's what they're doing. They have the structured data in the back end, and they're combining it and they're comparing it with the new AI ways of doing things. So that's exactly, they have unstructured clinical notes. So that's how they, possess it, because the benefit of large language models, not that this is a large language model. This is only 1 billion parameters. But anyways, the language models is that they can take these clinical notes and health records and enable them to actually develop predictions as well. So our approach is leverage recent advances in natural language to train large language models for medical language, and they call it NYUTron. So those of you, if you want to go and look at this paper, you should just search NYUTron, NYUTron, and that's where you can find this. And beautifully, they did it on 5 different tasks. So let me just show up the actual image where they do that. So they had these clinical tasks, in hospital mortality prediction. So that's extremely important. Anyone who's actually doing, making up a startup, that in itself, if you want to make a startup, this in itself is a one full-blown startup. Believe it or not, you don't have to do anything. Bin comorbidity index imputations, so that, for example, they use the Charles index. Anyways, what they are doing is basically understanding that what the comorbidity index is, and then 30-day all-cause readmission. And that is so costly to health systems right now that everyone wants to know, what is the prediction of readmission? Is it an extra day? Is it an extra education? Is it an extra reasonable near follow-up? Can decrease the risk of readmission. That will save hospitals, honestly, millions of dollars. So all of them are extremely good choices for doing this study. And then, of course, operational tasks. What do you mean by operational tasks? Operational tasks is basically, again, length of stay prediction. Again, this is very important because there are places in which we need to know that how the ambulances are going to be routed. If, for example, there's a thrombectomy stroke need within a community, and we can do that. And then secondly, if the patient is going to stay here for a longer period of time, then especially in a system like where they did, it was like NYU in 5 boroughs. So within that system, they can move patients around so that, in high frequency areas, they can have smaller length of stays and move patients, etc. So massive impact in terms of operations of hospital systems, especially large systems like they have. And when this where this study was done, and insurance denial prediction, of course, that is so important. Again, it is kind of annoying for physicians when we have to come. The debater tells us that, can you explain this if you're going to have, and write not encephalopathy unspecified, but encephalopathy due to metabolic reasons, and that small increase, incremental increase in the ICD-10 code lands them the severity that they need to say that the insurance that, hey, this claim should not be denied, and therefore a massive impact. Again, brilliant in terms of what they chose, in terms of why, what they tried to do. Anyways, as far as the study is done, let me go through that. So they actually went in all these five things, and then they shows neutron has our area under the curve of from literally five. I'm just gonna say 10%, which is the middle number, to 85%. Huge markup. Like, the traditionals were garbage in terms of way the large language models are able to do that. And again, they chose these examples. They trained, they're fine-tuned, actually, not trained per se, their model in doing these downstream tasks, and they were able to achieve a significant amount of predictability. Again, has real world consequences, as I told you before. This reliance on structured inputs introduces complexity. So freaking problematic, right? I mean, you have to go in, put in all these stupid boxes, and then come back. And therefore, if I'm writing a clinical note, it should be able to extract the patient has hypertension. It should be able to look at the blood pressure readings and put it itself in terms of blood pressure readings. So this structured data is kind of annoying and sometimes harder to find, because honestly, EHR search functions are sucky. Anyone who wants to do that actually is another big idea. Overwhelming majority of medical predictive algorithms being trained, tested, and published, yet never deployed to assess their impact on real-world clinical care. And that is such an important point. And one of the reasons that I'm bringing this study into limelight is basically that they did do that. Again, there are different areas in which they had lack, and they actually pointed out themselves nice enough. But we have to make sure that they actually, we need to see real world impact. If you're not going to study it in retrospective study, what's the point of doing the darn study? I mean, it's just becoming research. And this is basically bridging the gap between research and real world testing. And then eventually that real world testing is going to come to the next step, which is creating a final product for it to be used in mass market. They use the encoder based model. I'm not so sure about that. I'm not sure why they didn't use the decoder model like GPT-3s, etc. But it is their particular, foray. And then again, languages that can be integrated into real world. And that's one of the key hardest problems for any researchers, especially that are outside of these large universities where they can conduct these studies. But again, you need that real time clinical workflows and then approach them accordingly. So what they did was that they initially did, Lagone EHR, which is their electronic health record. That ended up creating NYU notes, and these are mainly the clinical notes. They extracted those and then took those notes and did fine tuning on them. How do you do fine tuning? Now, again, fine tuning is something, if you want me to actually do a full video on it, let me know. But there are multiple ways to do fine tuning. Actually, there's also in context learning. You can even do downstream tasks by even just prompt engineering, like if you're going to do for ChatGPT. And of course, there's basically what they did was the best one, basically. So fine tuning, in context learning, and then the last one is prompt engineering. And of course, there are multiple ways to do so. And then once they have done this, that's when they actually did the pre-training. So the whole thing was done into a large language model, and then mass language modeling was done. Mass language modeling is one of the ways that we train large language models. So it's 85-year-old female with past medical history of hypertension, and then they have to predict the next diabetes, and then they have to predict the next, and then they mask it. So they give you this data, and then they mask it, and then ask the AI generation to actually predict those masked words. And that's one of the ways that you can train these models as well. Anyways, so that's literally how they trained it. 7.5 million clinical notes. They were actually have a very temporal relationship of notes as well. So it was 1 to 10 years of clinical notes. And then the pre-training and the fine-tuning, both of them was happening and the downstream tasks as we discussed before. And then, of course, the mass technique as well. Overall performance on those 5 tasks were very good. Again, I'm not so worried about the actual task. What I really impressed me about this particular one was that they did real world testing. And what they did was basically retrospective study of let me see right here, retrospective study of readmissions. And that is one of the key things that they actually were able to do. And then physicians had a median score of 62%. So what they did was that they asked a bunch of physicians, about 20 of them, right? N equal to 20, to actually say that, okay, what do you think? Is this patient going to be readmitted? And then they were able to, look at future probability from this one. And again, as a physician, if I have this tool, there's intuition and there are other factors that we don't chart. I mean, lack of ride. My son is going to come fly in tomorrow, so I have to stay tonight. Or, we thought that they left with the family and apparently the son or the daughter had emergency and they had to go somewhere. So they're left alone in the house, did not take their medication. So there's so many other factors, of course, those human factors that we have to take into account. But at the end of the day, they were able to show that it definitely increased. And that's what I loved about this particular study as well. So this is, this is about the comorbidity. This is used the Charlson index and then the clinical notes. So this is the temporal AUC. These are the admin tasks, insurance denial, and length of stay. And then they actually do compare that if you use the NYUTron technique with clinical notes, this definitely significantly increased the predictability as compared to just that structured method. And again, that structured method takes a lot of human input, and that human input is a significant cost savings. If nothing else, honestly, if you use large language models to turn unstructured information to structured information, that's in itself a golden opportunity in terms of creating a new startup specifically in healthcare. Now, of course, the whole idea behind it is not to go through the whole paper. It is to bring into limelight that what we can do with these things. So what they do is further research is needed to optimize human AI interactions. And that's very important. Now, where we actually stand is, again, for most important things, we need to understand how we are going to be using these tools. And that is very, very important. And that is something that is up in the air. And then how we're going to use this into biases and other unexpected failure points, because let's face it, we haven't used it before. And just to give you an example, I don't know if you realize Epic EHR introduced that during the COVID times, they have this severity index. I forgot the exact name of it. But what they did was basically that they were predicting sepsis. So when they were predicting sepsis, before COVID, it was regular sepsis with bacterial infection. But the minute the COVID came in, the whole system went out of whack, because there was a complete model shift. That's the term we use, technical term, in which basically the whole data in behind it was not applicable, because most sepsis before COVID were dependent on bacterial infections that behave differently. And now we have a completely different set of physiological parameters in which this was a viral-based infection. So that particular model completely out of whack, they had to pull it away. So again, these kind of unexpected failure points that we don't know because of underlying data shift, underlying model shift, we have to make sure. And how do we constantly learn is, again, very important. Our approach is using a smaller 1 billion parameter model. Again, I think that this would be a better if they use a significantly larger model. Just to make you know that Facebook Llama is 65 billion parameters. I think GPTs the OpenAIs are all 165 billion parameters. The more you increase the size of the model, this is where you come in. You actually require 24 NVIDIA 100 GPUs and 40 GB RAM for 3 weeks, and fine-tune used 8 A100 GPUs for 6 hours. So again, the cost of GPU is always a big constraint. First is data. Glad they had it, and then the GPUs, and apparently they had it, but that was something that we constantly find out. I've talked about before, the rate limiting factor for any AI study, especially in large language models, is two. One is data, high quality data, and number two is GPU. The ultimate validation of an approach must be in a randomized controlled trial. Now, I'm not so sure about the word randomized controlled trial, because I don't know if you really need randomization, how you're going to truly do the randomization itself, because again, we are looking at, but honestly, even with this 1 billion small parameter, the amount of predictions they were able to do and the impressive, achievement they have done is very, very nice. And they deployed it in a live healthcare environment and demonstrated its efficacy, predicting 30-day readmissions while being integrated seamlessly into clinical workflows. And that is one thing that we have to frickin' start doing, because there's a huge difference, especially when you are even designing large language models or you are actually fine-tuning them. You will know that there's a lot more art that goes into it as compared to science. Well, glad you're here, and hopefully, who is actually listening, we're going to be talking about prompt engineering next, or I don't know how my video editor is going to post it, but anyway, prompt engineering for healthcare methodologies and applications. Stay tuned for the next video. Thank you.